Good afternoon and welcome to this iGEM webinar. My name is Neil Atkinson. I'm the Chief Executive of the institution, and I'm particularly delighted today that we've partnered with PenSpen, who are a global service provider for the energy industry, particular emphasis on asset integrity, asset management, and gas metering. So we have a truly expert lineup today to talk to us about the role of the gas networks in decarbonisation. And as we well know, that's a real challenge, as the legal obligation on the UK to achieve this makes the imperative for the transition to happen. And there will be many challenges involved with this. Today, no doubt, we'll be talking about transportation, issues like compression, materials, leakages, and much else besides. So the team that will take you through this from PenSpen is Peter O'Sullivan, the Chief Executive Officer, who has a very strong track record in oil and gas engineering and project management. To Nigel Curson, the Executive Vice President of Technical Excellence, with over 30 years of experience in the sector, and John Downer, a Senior Project Manager. So as regards the session today, we are using the platform, which means that all your microphones are automatically muted, so there'll be no disturbances. We will be taking questions after all the presenters have spoken today. So there is a facility on your screen here to ask those questions. So please click the tab and send those to us, and we will publish them and hopefully get to answering some of those questions with the team. If we are unsuccessful and there's lots of questions from a timing point of view, we may well find a way to get those questions answered to you in due course. Should advise you that this session is recorded and will be available also after the meeting on iGEM TV. So just check your emails tomorrow. So with that said, welcome to Peter and the team, and perhaps you could tell the iGEM audience about the role of the gas networks in decarbonisation. Thank you.
Thank you very much, Neil. Thank you for that introduction, and thank you to iGEM for the opportunity to discuss what I think we all agree is a very important topic today. If we just move on to the next slide, I'd like to give you an overview of what we want to cover today. So first of all, putting it all in context, what are the challenges for the UK's legal obligation now to achieve net zero? And what's the role of hydrogen and the UK gas networks in facilitating that? We'll look at hydrogen production and transportation, particularly with regard to the challenges that these present to the UK gas networks, and also the future of green hydrogen and how that might look, what role that might play, and then just finish off briefly with a few words about what's needed to make this transition happen. So I'll start. First, the UK climate change objectives. The UK is one of a handful of countries globally that have signed into law the objective to achieve net zero emissions by 2050. And progress in achieving this has been very good since the Climate Change Act was introduced in 2008, and the UK is on track to meet its third carbon budget. However, the outlook for the fourth and beyond that is more challenging, because we're now trying to abate sectors that are harder to reach. But hydrogen can potentially play a very important role in addressing these sectors, and by implication, the existing and future gas transmission and distribution infrastructure also will be critical. Next slide, thank you. So just looking at progress to date, over the last 10 years, the UK has made very good progress in reducing greenhouse gas emissions by over 24%. You can see on the charts on the right, this has been largely driven by the power sector, where renewables and natural gas have significantly displaced coal for power generation and have led to significant reductions in emissions from the power sector. However, in other sectors, progress has been much more limited. In industry, emissions from industry, after initially good progress, they've started to plateau now. And for buildings and also for surface transportation, emissions, progress in reducing emissions has been pretty limited, to be frank, over the last 10 years. And the reason for that is that in each of these sectors, they present challenges in terms of reducing emissions that are harder to address. Next slide. So we just take a look at each of these to understand a bit more about what they are. Industry represents about 25% of total annual UK carbon dioxide equivalent emissions, about 104 million tons. And a lot of that is coming from the need for heat in manufacturing processes. And industrial heat is difficult to electrify economically. So that's a specific challenge that needs to be addressed. For buildings, there are 25 million on-gas residential, public and commercial buildings in the UK, which generate almost 90 million tons of carbon dioxide, again, used for heat. And retrofitting heat pumps to all of those buildings would be an absolutely massive task. So in each of these cases, hydrogen as a fuel to switch to plays potentially a very important way to reduce these emissions, which would be harder to reach otherwise. Next slide, Annie, thanks. Looking at surface transportation, again, about 25% of UK annual emissions, about 115 million tons of CO2 equivalent. About 80% of those emissions come from passenger cars and light vehicles, and there's a well-established route to decarbonisation of that sector through the electrification of those vehicles. However, for heavy goods vehicles and buses, heavier duty vehicles, which represent about 20% of emissions from the sector, the electrification of those is harder, and it's unlikely to be economic even into the 2030s based on current research because of energy density and weight in batteries. So hydrogen electric fuel cells are a potential route to decarbonize those heavy vehicle sectors, which would enable us to achieve the 2050 net zero objectives in a timely way. Next slide, Annie, please. And then finally, the power sector, although it's made good progress to date, has a specific challenge in terms of the variations in seasonal power demand. So in the UK, peak demand is in the winter, and last November that was around just under 40 gigawatts of power capacity, versus in the summer, May this year, it was about 25. So that represents a gap of about 13 gigawatts of capacity. Now currently, most of that, about 9 gigawatts, is made up in winter from natural gas and coal. So fully decarbonizing power will require finding a carbon neutral alternative for unabated natural gas and coal. And that's going to be difficult to do on renewable power alone, given their intermittency. So power storage is going to be most likely part of the solution, and hydrogen has a unique potential to address this, to store power in large quantities for long periods of time. Next slide. So to sum up, we, in order to achieve our net zero goal by 2050, we have to make a lot more progress in industry, buildings, and transportation, which are the largest emissions sectors now. Switching fuels from natural gas to hydrogen will definitely have an impact in industry and buildings, and will enable us to decarbonize those sectors relatively quickly. And then potentially using hydrogen fuel cells for vehicles will help to address that sector. And hydrogen is probably one of the only ways of storing power economically over seasons to balance seasonal demand variations. So hydrogen clearly has a very important role in achieving our net zero goals. And likewise, therefore, the UK gas networks are going to be critical for its production, storage, and transportation. So to look into that in more detail and the implications, I'm going to hand over to Nigel. I think you're on mute there, Nigel.
Thank you very much, Peter, and good afternoon, everybody. Next slide, please. When we talk about hydrogen, we generally refer to it in terms of colours, and the way that the hydrogen is currently produced. First of all, there's no naturally occurring hydrogen; we have to make it. And the colours we're normally talking about or are currently produced are coal, which we refer to as black hydrogen, lignite, which is an earlier form of coal, as brown hydrogen, and then grey hydrogen, which is hydrogen from natural gas. None of these currently have CO2 sequestration, and they currently emit about 830 million tons of CO2 into the environment, which is something like more than 2.5 times what currently the UK emits. It's used for production of ammonia, for hydrocracking in refineries, and there are small amounts of it that are actually traded. So everything we're going to be talking about today really is about blue hydrogen, which is from fossil fuels with carbon capture and storage, and green hydrogen, which is from renewables. So when we talk about the hydrogen economy, we're talking about hydrogen as a predominant fuel, which is sourced and traded as a nationally or even globally. So next slide, please. So the question is, how do we make it? And really, there's only two real serious methods right now, and it's from natural gas using steam methane reforming, or SMR, and this produces hydrogen with some impurities and CO2 as well. The other way, which is electrolysis, which is completely green, no CO2 involved and no impurities involved as well. But really, electrolysis would need to massively scale up if we're going to produce hydrogen at the scale we need it, and it's really in its formative stages and doing it at scale. So you can see from the graph on the right, SMR from gas with carbon capture and storage is by far the cheapest way, and really the only practical way we're going to be doing this in the near term. So, but of course, green hydrogen is very, very important for the future. So green hydrogen will slowly replace blue hydrogen as things progress. Next slide, please. So if we know how we can produce hydrogen, it's going to be SMR initially, certainly, with CCS. So it's going to almost certainly be placed with large plants close to storage and close to where gas imports are, because building pipelines to storage is expensive. So how do we get it to users? So hydrogen can be transported as a compressed gas in cylinders. It can be supercooled as a liquid and transported in a truck or a ship, or it can actually be transported as a different molecules completely, which would be ammonia. But really, in terms of cost and efficiency, the volumes we're talking about, pipelines are really the most cost effective. And it's important to understand that we've actually done this before. Coal gas in the 1970s was actually about 30% hydrogen, and that was a UK-wide network. It wasn't actually used for heating at that point. And also, we have already about 1,600 miles of pipelines in the US and Europe already operating. So, next slide, please. So, completely synonymous and integral with hydrogen production, we have CO2 transportation. We're producing vast quantities of CO2 to be carbon neutral. We need to transport it to a place of storage, and it can be done as a supercooled liquid in a ship. But really, again, pipelines is the most efficient way of transporting the volumes we're talking about. So, and some important facts around that: the critical pressure. If we're transporting CO2 as a liquid, the critical pressure is around 74 bar. And in fact, impurities from SMR actually drive this up to 100 bar. And some CO2 pipelines have been looked at are about 140 bar. Typical, the highest pressure of UK onshore pipelines is about 70 bar. So this may actually affect the opportunity to reuse existing onshore infrastructure for CO2 transportation. However, some of the offshore lines I'll be designed if it, particularly if it's for dense phase, 160, 170 bar, 180 bar, so it can be reused, and that is being currently proposed in a number of places. So also, if CO2 is actually post-combustion captured, typically this is a very low, if not atmospheric pressure, so very significant multi-stage compression is required to get it up to the 100 bar, and this uses a vast amount of energy, a lot of energy. And also, when it actually arrives at the reservoir, some of these reservoirs are actually blown down to quite low levels. Some of the ones we've looked at are 20 bar. So you have to go from something like 100 bar to 20 bar, which involves adding a lot of heat back into the fluid to avoid very low temperatures on the wellheads. So doing this is very expensive. It adds something like 39 to 50% on the cost of producing electricity, and between 17 and 44% on the cost of SMR. So it's an expensive operation. Of course, CapEx advantages in reusing equipment, which will be pipelines and platforms, particularly in the offshore oil and gas sector. So next slide, please. One thing that's very important to understand about gas and pipelines in general is that pipelines, in terms of transporting energy, are much cheaper. Something like 10 to 20 times cheaper than the equivalent cable for the same amount of energy. Also, they have a much higher capacity. Pipeline or cables have something like 1 to 2 gigawatts capacity, whereas a hydrogen pipeline bit has 15 and 30 gigawatts energy capacity, so significantly different. So also there's a big difference in terms of losses. Cables are very known for their I²R losses. Pipelines have very limited losses in comparison. So, and also pipelines are a lot more flexible. Hydrogen can be actually stored in the pipeline. It can be line packed, and this is used in the existing transmission system. And also hydrogen can be stored in underground caverns, and it's something like 100 times cheaper than batteries. So pipelines are a very efficient way of moving energy around. They are now, and they will be certainly with hydrogen too. Next slide, please. So talks a little bit about the UK gas networks and some of the projects that are currently underway. Next slide, please. So there's a lot of progress in terms of hydrogen in the UK. Many governmental bodies looking at it, many organisations, industry, private enterprise. These are some of the very important projects that I've picked just to talk very briefly about. And the ones on the left really are focused predominantly, certainly to start off with, with blue hydrogen from SMR. And then on the right, far right, we've got things more for the future, focused on producing green hydrogen. In the middle are projects which are focused on the user end. In other words, they can accommodate any kind of hydrogen. So just quickly on the left, we have a number of what we call industrial clusters: HyNet Acorn, Wales, Net Zero Teesside, and Zero Carbon Humber. And Hyper is a project where a very efficient SMR is going to actually be piloted. And in the middle, we've got H21, which is looking at supplying mixtures and even 100% hydrogen to distributing it to cities. High Motion is about hydrogen for transportation. Hydroplay is actually underway, and this is providing a mixture of hydrogen to Keele University, to residential dwellings. And on the right, I've just talked about Dolphin. Dolphin is actually offshore wind, which has electrolyzers next to the wind turbine, produces hydrogen directly, and transports it to the UK network. So, next slide, please. So when we talk about industrial clusters, this is roughly 25% of UK emissions, so extremely important. And it's thought of really to be the first step, or first very important step in decarbonisation. And it can be done because they're clusters of industry that are close to sites where you can easily make hydrogen with SMR and also dispose of the carbon that's produced. And just very quickly going around the coast, we've got the Acorn project in Aberdeen. That will also be a sequestration site for carbon produced at Grangemouth. On the east coast, we've got Net Zero Teesside and Zero Carbon Humber. Liverpool Bay on the west coast. These are all using existing oil and gas assets. South Wales, aimed at the existing steel industry there, which is a big emitter of carbon dioxide. That's kind of differentiated from the others. It doesn't have a CCS site nearby. They're planning on actually transporting this by ship as a supercooled liquid, potentially up to the Acorn project. So that's industry. So what about the rest? Next slide, please. So hydrogen for heating is incredibly important, whether it's residential, commercial, or public sector, and this represents something like 28% of UK emissions. The majority of our homes are gas-fired, and also something like 75% of energy is provided to homes via gas, only 25% by electricity. From an overall efficiency perspective, we know heat pumps have proven by research to be a very effective way to do it, but to retrofit these is very, very expensive, and also to upgrade the network to provide electricity to them again is something more for the future. A lot of infrastructure would be required, particularly if you consider electric vehicles are also likely to be very predominant, also requiring a higher level of electricity to provide to domestic dwellings. District heating is excellent, highly efficient, probably a very good solution for local areas close to waste heat. So really hydrogen is the easiest in terms of maximum reuse of existing equipment, and reuse really means radiators within houses, distribution piping. It works really well with the existing or repurposing the existing gas network. So next slide, please. And transportation. Total UK transportation is something like 36% of UK emissions. 62% of trains are currently not electrified, and even on electrified tracks, a lot of the trains that actually operate on electrified tracks are actually diesel to cope with the very high loads in goods transportation. So the majority of emissions are actually from passenger cars and light vehicles, but we know that a lot of these are going to go over to electric. But the heavier goods, buses, trains, etc., will take much longer to get over to electric. So hydrogen is an excellent fuel source for these. So again, the network is going to be a very, very good way of actually transporting hydrogen to terminuses and filling stations. So next slide, please. The other aspect of transportation, of course, is transporting hydrogen to storage, and also transporting CO2 to not storage, but sequestration. In other words, we don't need to get the hydrogen back again. I'm not going to go too much into hydrogen storage because John will talk about that. But in terms of the UK is very well endowed with storage. We have the capacity for 78 gigatons, which is over 500 sites. So if we take the total UK emissions right now, which is about 312 megatons, we've got something like 200 years worth of storage. So certainly relying on blue hydrogen, we have plenty of time to get us to green hydrogen in terms of carbon storage. These will initially be former oil and gas fields. That's predominantly the choice. But we know from extensive research on this that actually the larger storage area might be saline aquifers. Next slide, please. So in terms of the UK gas networks, what does this mean? And when I'm talking about networks, I'm talking about the onshore extensive distribution system we have, but also the offshore oil and gas network as well, some of which is now being decommissioned, which can be repurposed for the purposes of decarbonisation. So we know that pipelines are the lowest cost form of transportation. So the network will have a very important role in decarbonisation. The industrial clusters are actually reasonably self-contained, but do need connection for security of supply, because we need very, very high reliability. So the network really is an excellent for domestic supply. We know it's got a large network of connections to domestic dwellings. We've got hydrogen and CO2 transmission and renewables. We can actually produce renewable electricity offshore, immediately convert it to hydrogen and transport it into the UK system. For security, balancing supply, and also energy storage, we can actually use the UK transmission system, and in fact some blind end pipelines in offshore can also be used for storage. So we've got 7,500 kilometers roughly of transmission and 250,000 kilometers of distribution pipelines connected to 25 million customers, over 85% of homes are actually connected. So in terms of the networks, the requirements will change, and they will be quite dynamic, changing in steps as we move towards 2050 and beyond. Some elements will need to be replaced, and some will be reused. Of course, we'll reuse where possible. So, next slide, please. So I just want to talk now a little bit about the challenges, some of the challenges for the gas networks. There's a few that we need to address. Next slide, please. So compression is certainly an important one. Certainly compression is important for hydrogen. We need to get up to a pressure where we can transport it. Now the compressors of choice for natural gas and existing working on the network are actually centrifugal compressors. But when you actually think of a centrifugal compressor working with hydrogen, the tip speed of the rotor needs to go something like 3.8 times the speed, which actually puts 14.4 times the stress on the rotor. It's the square of the speed for a centrifugal compressor. And also, you may be aware that hydrogen actually can dissolve into materials and cause embrittlement. So this means that we have to restrict the temperature of compressors. Currently, the interstage temperature can be over 100 degrees and even 150 degrees, but with hydrogen, it needs to be limited to something like 65 degrees. So this means we need more stages in compression. So this really means that the existing compressors are not really going to be suitable for operating with natural gas. There are a number of alternatives, but there really is some optimization required to develop efficient, optimized compressors for the transportation of hydrogen. Next slide, please. Another challenge is with the heat value. Hydrogen from a specific heat capacity basis, in other words, on a mass basis, has a very high calorific value, but on a volume basis, it's very low compared with natural gas. In fact, the calorific value or the heating value of hydrogen is 1/3 of natural gas. So in terms of volume multipliers, if we have 20% hydrogen, then we need something like 1.2 times the volume of hydrogen. Or if we're talking about 100% hydrogen, it's 3.4 times the volume of hydrogen. So this means we've got 3.4 times the velocity, 3.4 times the volume. So this implies significant constraints with the reuse of some infrastructure. And if we want to maintain the same energy density, we have to increase the pressure by a factor of 3 roughly. So that will be 200 bar for a typical pipeline. There is some flexibility in the distribution zones, but some of the transmission systems are already constrained. So next slide, please. Another important issue is materials. As you know, carbon steels are predominantly used for the construction of pipelines because they are cheap and strong. And there are about 1,600 miles of existing pipelines. Some of these are actually operating at high pressures, 140 bar. But the problem with use of hydrogen and steel is that the hydrogen dissolves into the molecular structure, into the lattice, and actually produces embrittlement. So this means you can only use, or so far, the experience has shown you can only use very low grades. So grade B, X42 and X52, these are very low strengths. And in fact, during the design process for an appreciation of embrittlement, in some cases, the stress is actually limited to 30% to 50% of the specified minimum yield strength. So there are guidelines. European gas industry has guidelines, and also there's an ASME B31.12 guideline for the design of hydrogen pipelines. So bearing in mind that some of these new pipelines are going to have to be operating at 200 bar to get the same energy density, if you actually work that out for X52 and a 36-inch pipeline, you'd end up with a wall thickness of about 35 millimeters, which is very, very thick indeed. Typical 36-inch gas pipelines are more like 19.1 millimeters, so expensive. So there is a lot of industrial experience with hydrogen, but there's not much complementary data for use with hydrogen with high strength steels, and I know this work is currently being done in various places. So again, you know, this does create potential issues with reuse of existing infrastructure. There is some work being done on using fiber reinforced polymers. There's a possibility to produce these in half a mile lengths, which are not susceptible to hydrogen embrittlement and can withstand these very high pressures. So potentially something for the future. So next slide, please. The other challenge is leakage. Hydrogen has a very small molecular species size, so it actually is very good at diffusing through materials and producing leaks, or producing through connection points. So this is some experimental work that was done in the Americas. So this is a distribution system operating at 4.1 bar, operating at 4.1 bar pressure, and you see it at 0% hydrogen or just natural gas. There's very little leakage. But if you look at 100% hydrogen on the far right hand side, it's something like 7 times the leakage rate. So this is not necessarily an issue, but something to be very much aware of. And I know this is something which is being looked at again right now with the current research. Next slide, please. Next issue is risk. The plot on the left is individual risk per year as a function of distance from the pipeline. Now hydrogen has a very high buoyancy, so in an incident, hydrogen will actually rise up into the atmosphere very quickly, which means the radius of impact is much less. However, if you're close to the incident, then the actual risk is higher. So when it actually comes to it, with new pipelines or pipelines operate at different pressures, or different materials, or higher strength steels, or lower strength steels with greater ductility, the risk will be different. And I know again there's a lot of work being done at the moment. So not necessarily more or less, but certainly different. And this is a very important topic of research. So next slide, please. And the other aspect or challenge is dealing with the mix. We know that there's a lot of work being done on mixing hydrogen, something like 5 to 10% being provided to domestic dwellings, and a lot of equipment that's currently being operated with natural gas will continue to be able to be used with 5 to 10% hydrogen, or even 20%. But this is not going to resolve the emission issue, really. I mean, we need 100% hydrogen. So this is a way of getting hydrogen going in terms of production, but in the end of the day, it won't solve anything. So as a transition to hydrogen, we need to have a mixture, and we're going to have mixtures of 100% hydrogen. We're going to have some pipelines with mixtures of hydrogen, some with natural gas, some with biogas. So how do we manage all these different requirements across the network? How do we transition? So deblending is a potential technology to help with this. This allows us to actually extract hydrogen from the mixture, which can be supplied to users that have 100% hydrogen. Also, there's a need to relax on our current entry standards. Currently have 0.1% hydrogen. Clearly, we need to change that if we're going up to 5, 10, 20%. Also, how to bill. Very likely, customers all over the UK will be getting different products of different calorific values. Right now, it's all on the same basis, flow weighted average calorific value. This is clearly going to be unfit for purpose. So there are various ways being proposed. Most extreme way is that we measure calorific value at every user point, which obviously will require a lot of investment in equipment. Next slide, please. This is my last slide, and this really summarizes the position with respect to networks. This is produced by a European collaborative group, Marco Gas, and it's a very useful narrative. On the vertical scale, we have between 0 and 99% hydrogen, or 100% hydrogen. On the bottom, we have all the different issues, and you can see the ones I've highlighted. Pigging stations, issues with seals that would certainly need to be replaced. Compressors we just talked about would have to be replaced for 100% hydrogen. Because of the embrittlement problem, probably wells on storage would need to be replaced. Ultrasonic meters will go up to 20%, but beyond that would need to be replaced. Fittings, again, potentially issues with leakages. Gas turbines, again we've talked about, and condensing boilers, will work as they are up into about 20%, but beyond that, really, you need a replacement. So that's my final slide. So I will hand you over to my colleague John.
Thank you, Nigel. Good afternoon, everyone. If we can go to the next slide. So we've heard from Nigel in discussing industrial clusters that predominantly we feel the production of hydrogen will devolve to the main process of the moment, SMR, which has the benefit of producing hydrogen at large volume, but a very great downside of producing additional carbon dioxide, which will need to be dealt with via sequestration. The main alternative method currently developed of producing hydrogen is using electrolyzers to and a renewable source of energy to generate green hydrogen. It's called green hydrogen because there is no associated production of carbon dioxide and therefore no need for sequestration. So, keeping to the focus of this presentation and the title, the role of the gas networks in decarbonisation, we feel, given our opinion, that green hydrogen could develop as a series of regions around the UK with local networks, also connected between the regions by perhaps export pipelines for hydrogen, or export pipelines connecting deeper into the network across the UK, linking up regions, or these blue hydrogen clusters. There's no reason why a green hydrogen can't interface with a blue hydrogen cluster. So green hydrogen will develop in local regions, we feel, and be able to connect out of that into the wider UK region. Next slide. So what would a region look like? In this graphic, quite simply, we've got on the left the means of production, which in the UK will be predominantly from wind energy. Doesn't necessarily have to be, and of course in the current climate with increasing solar production in the UK is also growing too. Whatever the source, renewable energy, electricity will enter electrolysis to produce hydrogen. The technology for that is in development to improve the outputs. Any excess hydrogen that can't be consumed immediately will go into storage, which could be above or below ground. And then for actual use of hydrogen in the local green hydrogen region, a variety of uses are foreseen. And in the closing slide, we'll show you an example of a green hydrogen region actually in practice at the moment, but which includes some of these. There may be a local existing gas network in the green hydrogen region which can be adapted for hydrogen transmission. Outside of the local region, export pipelines will connect different regions, blue clusters, green hydrogen, other regions, and into storage. And some of the hydrogen will be consumed by the large transportation elements, which may include shipping or lorries using fuel cells or ammonia. Next slide. So what we'll do now is, keeping that graphic in mind, is go through each of the main elements. So for renewable production of green hydrogen, in this slide we recalled from DEC the rapid escalating growth in renewable energy generation across the UK, of which offshore and onshore wind is highly significant fractions. And according to more recent research by Aurora Energy, there's an estimate currently that up to 50% of national demand could come from hydrogen generated power by 2050. But for this to happen, the growth in renewable energy, which is recorded in that graph, will need to be not only maintained but accelerated in order to produce the renewable energy inputs to generate sufficient hydrogen. Now, the actual numbers to produce hydrogen from renewable sources are contestable and the technology is rapidly changing, but a recent reference for a project in Australia had for an input of between 1.5 and 2 gigawatts of renewable energy, a production of 1 gigawatt of hydrogen. So to replace natural gas, we need to build, based on current estimates, around about 6 gigawatts of new hydrogen production capacity per year, which, using that indicator from Australia, implies a huge, way beyond the current investment of renewable energy power to be produced year on year. So the challenge is enormous, although the upside potential of producing hydrogen with no carbon is obviously highly attractive. Next slide. Certainly for myself and for many of us, the idea is that turbines produce energy continuously, and when that power is not going into the grid, it could be used to productively to generate other things such as hydrogen. But this is in fact a bit of a fallacy. There isn't simply just enough surplus energy generated to be useful in producing sufficient hydrogen, and using curtailed wind as a proxy for surplus energy, even if by 2050 that curtailed energy reaches 75 terawatts, it could only replace a fraction of the UK domestic heating demand. So we need to invest in renewable wind energy for electricity production, but also if we're serious about green hydrogen, there'll be a commensurate need for additional investment in wind energy just to produce hydrogen. Next slide. So currently in this graphic, it's quite interesting just how many onshore wind energy developments there are around the UK, as well as the highly significant offshore. One of the most interesting things that's happened in recent times is the reducing cost of wind energy, which has continued to make it attractive. But to repeat the previous slide message, although this looks an extensive network, much more investment will be needed just to supply the predicted growth in green hydrogen demand around the UK. Next slide. So from renewable energy, how is the hydrogen produced? Fortunately, there's a number of electrolyzer technologies in existence, but proton exchange membrane technology seems that the most topical of the moment for renewable, because it's highly efficient and it works well with intermittent power inputs, which are typical of what one can get from wind energy. And it's also highly efficient. Current technology indicates efficiencies of over 80%, and there are calculations which indicate this technology could reach as much as 92%. So those are all positives for the future, which would be needed to accelerate and increase the volume of hydrogen production from green hydrogen sources. Next slide. Hydrogen storage has been mentioned by Nigel, and again, hydrogen is viewed as an interesting potential fuel and an alternative to natural gas, but viewed in terms of pure energy, it's a highly interesting product to view as a means to store significant volumes of energy over longer periods of time, and with an ability to amend the drawdown of energy to meet the external power demands. And this would be particularly useful in the winter months, where increased hydrogen storage will enable a flattening of the winter peak and reduce the need for additional investment in renewable offshore and onshore wind energy. And it also additionally has great capacity in terms of ability to be used around the UK, as Nigel had mentioned, for saline and salt cavern storage, of which the UK is fortunately blessed with a large number of potential sites. Next slide. So in this slide, we indicate some of the current areas where there is potential, and it's interesting to note some of the future storage areas are actually near large conurbations in the south, and a distribution like that will assist their use to supply an integrated energy grid around the UK. As regards the transmission network, any new storage sites will require new pipelines to reach into the storage and exit the hydrogen from storage. And as Nigel said, those pipelines for pure hydrogen will have different chemical characteristics in the materials and design than the traditional methane gas network. Next slide. So to take and combine those ideas into a current example, in the Hebrides, there's been, albeit at a small scale, development of a small hydrogen network which integrates all the elements of the slide at the start of this presentation. Renewable offshore energy, feeding electricity to an electrolyzer. There's above ground storage of compressed hydrogen. Some of the hydrogen is used directly in a local grid, and other hydrogen feeds converted cars and other vehicles on the island. And there is the possibility of export from the island via pipelines potentially, or via ships. And there are plans to convert the Hebridean ferry to use hydrogen fuel cells, or, which entirely seems more appropriate for ships, use of ammonia. So this is a current example in practice, and there's also a research facility on the Hebrides looking into continued and expanded use of hydrogen. Next slide. So wrapping up, that for this section, green hydrogen is highly attractive because it comes producing hydrogen, but is carbon free, unlike the alternative major process. There needs to be increasing investment to improve the efficiencies of electrolyzers, although they're already high. There will be a need to enlarge the investment in renewable energy to be commensurate with the growth predicted for hydrogen. Around the UK, we may develop a number of green hydrogen regions, exporting surplus hydrogen to storage or to other areas requiring hydrogen. And we envisage the networks will involve in the future a hybrid of parts of the existing system for lower pressure hydrogen transmission, and perhaps new purpose-built high pressure dedicated hydrogen pipelines taking hydrogen around the UK to main centres of demand. With that, I'll hand over to Peter for our conclusions and wrap up. Thank you.
That's great. Thank you very much, John. So if we can just skip on to the next page. So I think both Nigel and John have outlined the scale of the challenge and the scale of the investment that's going to be needed to really capture the opportunity that hydrogen presents. And so the question is, how do we incentivize that investment? We've seen in renewable power that the renewable obligations and contracts for difference have had a very positive effect in stimulating investment in renewables. And already in the hydrogen sector, there's in the region of £100 million being invested in pilot projects that we've outlined earlier on. But really, to get to full decarbonisation with hydrogen, it's going to require billions. And ultimately, the government will have to create a market for hydrogen and a framework and the incentives for investors to invest in that market. And we know that the government is looking at this and is looking at publishing their view and their model sometime next year. And what's on the table in terms of how this is going to be managed? Well, a regulated asset base model, one that we're familiar with, would be potential for CO2 infrastructure, hydrogen transmission and distribution infrastructure. The offtake support models that we've seen in the renewables, also contracts for difference and so on, will help to support pricing for hydrogen and carbon dioxide, so they may be part of the story. And then also potentially obligations on suppliers or users of hydrogen to include hydrogen in part of their supply might be part of that. But whatever the model is, it's critical to get that in place soon so we can start to stimulate investment in the sector. And we're looking forward to seeing what the government brings forward next year. Next slide, please. So to sum up, clearly hydrogen can play a critical role in getting to net zero and addressing some of these challenges we face in the harder to reach sectors. Initially, we're going to be looking at large volumes of hydrogen produced via SMR, blue hydrogen, and gradually we'll look to transition to green hydrogen. But in either scenario, the gas network will be important, although it's going to look different in terms of its structure and its composition. And there's clearly a number of engineering challenges that need to be addressed to really seize the opportunity, as well as the investment framework and public policy support to make the investment happen and move things forward. But a very important issue, and I think there's work to be done to capture the opportunity, but it's there, and it will significantly play a role in helping to get to net zero.